So, colleagues, good evening, everybody. Today we'll have a webinar around the Kaggle competition called Santa challenge. So it was quite interesting and unusual challenge. By the way, we have such kind of meetings quite regularly about different activities in bioinformatics, and you can find the information in our Telegram or Twitter, and video records will be on the YouTube channel. You can find the information here. And if someone wants to share any kind of experience, please welcome. We are very informal. We are very kind of, we'll be happy if someone will share his experience on any topic related to data science, bioinformatics, and mathematics, and whatever. Okay, so about this competition. This competition is a little bit unusual for Kaggle because it's not so data science, it's not so machine learning, but Kaggle creates, it's more like a combinatorial optimization. This competition Kaggle organizes each year, something around the new year, and all of them called Santa, and you can see Santa Claus here. So this year competition was, and they sometimes short. This competition was short, about 1 month, a little bit more. So the prize was a total $50,000. There was more than 1,000 teams participating, and it was quite a challenging competition. Okay, so for those who did not participate, let me just introduce what was the task about. So we can look on this task in 4 different ways. The first, the most simple, we need to solve the puzzles. It's not only the standard Rubik cube, but it can be very big Rubik cube, or even some other different puzzles. Master ball, globe, rest, so on. Yeah. Of course, we were not given these mechanical puzzles. Everything was in computer. And we can reformulate the task in different ways, which kind of more suitable for computer analysis. So one of the reformulations is the following, that we have some set of matrices given to us as say fixed for the moment, and we have 2 vectors. Then we need to find the sequence of matrices such that we apply, here should be V1 to the first vector, and finally should get in the second vector, where these matrices should come from this given set. They kind of represent the moves of the puzzle. The second reformulation is about the same, but you need to but we kind of substitute the matrices by the permutations. And the same, we have 2 states, and we need to find the sequence of the permutation such that this sequence converts one state to another. Actually, we can think also about this task in the 4th way in quite different, that we need to okay, yeah, sorry. So we need to find a short path between the 2 nodes on the graph. That is another way how we can think about this task. But actually, this graph is extremely large. It's not given to us. We only have its theoretical abstract description as a Kelly graph for appropriate groups. I think those who participated, this is very clear, but if someone have not participated in this challenge, is it clear? Alex, is it clear for you, for example?
Of course, crystal clear.
Wow, super. Anyway, guys, don't hesitate to ask the questions if any kind of. So, okay. What is the more simple way to solve such kind of puzzles, and why it will not work in general? The most simple way, just a kind of brute force. So we can take one state and construct all the states applying these matrices or permutations or moves one time apply 2 times all possible 2 moves, apply 3 times, and so on. And we can do it from the final state also. And at some point, we should get the intersection because all these puzzles are finite. When we get the intersection, then we found the kind of some path which connects the 2 states. Why this solution will not work in general? Because these puzzles are exponentially hard. So, I mean, the number of states grows exponentially. For example, for the standard Rubik cube, it goes each time 13 times. And so it's impossible to store all the states in the memory of any computer. Now let me give some examples of the details. So how this was given to us, how this task was formulated on Kaggle. These are some examples. So we have puzzles of different types, for example, 2 by 2, another globe, and different cubes, different globes. For each of them, we have the solution state and the initial state. So you see they are kind of permutations of one of the other. And we need to find the sequence of the permutation such that initial state will finally go to the solution state. So the permutations moves we can also see in what was also given to us. So we can think of them as a permutation matrices, for example, or as a permutation. So here is, for example, the permutation matrix representation of the moves, one of the possible moves. So this is the matrix which have only 0 and 1, and in each row we have only one unit, and all the other zeros. These matrices are called permutation matrices. And actually, there was some given hint to us from the Kaggle, from the organizers, that we were given some not optimal solutions. This represents the sequence of moves. So R0, F1, these are some notations for the moves, for the matrices which we discussed before. And Kaggle provided us that this is not optimal solution. If you apply these matrices of permutations to the initial state, finally you get the final, the desired solution state. But the number of moves here was, for example, you see in the given solution, for example, in the first 600, but actually people immediately optimize this simple puzzle to 24, for example, or something like that. So the people kind of initial solution was something like 10 times worse than people achieved finally. Now, a little bit, let us speak about why it is interesting and important for some mathematics. So just to give you some example that in mathematics, we are interested in something what is called diameter of the graph, or in this puzzle language, it's called God's number. The number of the moves such it will solve any kind of puzzle. Whatever you scramble, in this number of moves, you will solve it. So on the graph language, this is diameter. That means the most far distant point, the distance to the most far on the graph point. And so in mathematics, actually, there are many conjectures about this, which are still unsolved. And people and even such geniuses like Terry Tao, they're working on them. To give a short example, that for example, for Rubik cube, for 3 by 3, this number is known. But 4 by 4, it's already unknown. So mathematics now is not that much developed to easily solve this task. Also, for cubic, there are quite good estimates of the diameter, n squared divided by log n. But still, this constant is not kind of sharply known. The most famous conjecture in this field is the following, that if you take G, some group, finite, well, simple, let me don't explain what is simple, but the conjecture says the following. whatever sequence of generators you choose, this is allowed move, the number of the diameter will be less than logarithm of the size of the group in some power, and this power doesn't depend on the group. The conjecture was formulated in this way in 92, but it was known before in some special form, so it's a kind of famous folklore conjecture. So some recent results, for example, Harald Herifgott made a breakthrough in 2008. He proved this conjecture for SL2 for 2x2 matrices. There was some follow-up works, including Tao and others, where they extended this for some larger matrices. But still, as far as I understand, in full generality, the conjecture is not solved yet. And so what will be interesting is to apply modern machine learning methods and to give another look or kind of better results in these problems of the diameter and the God's number estimation. So since AlphaZero was successful, I think, well, kind of that should be possible. And so everybody who wanted to join this activity, please let me know and we'll think how to proceed. And thank you very much. And now, anyone have any questions, comments, suggestions, or we will move to Pavel's presentation? Okay, so if no questions, Pavel,
shall I continue or Vladimir?
I can,
sorry,
if you
no,
don't
Vladimir,
mind.
yes, Vladimir, sorry.
Sure. Yeah, I'm also quite fascinated by the idea of applied machine learning, and I had that in mind. In fact, I tried it a bit. It didn't really work, although I believe it's the right way, because the approach would be independent of puzzle. You just set it up, you feed it allowed moves and solution state, and hopefully it works for any type of puzzle. However, I started with something simpler and then switched to algorithmic approach. And yeah, basically, I worked only on that path during the competition. Yeah, sorry, my teammates. It's real nice to see you, but my talk might be a bit boring for you because you probably know it already. But for any other, I made this notebook with optimization of any solution. Maybe quite unique thing for this competition on Kaggle was that we had some solution as a sample solution, and you could actually start with that and building on top of that, optimizing it, gain a better solution. Usually you can't really do it in other competitions. So what you can do? Well, one very simple idea is that some moves cancel each other. For example, if you make some move with Rubik's Cube and then you just move the same face in the opposite direction, you basically change nothing. So if you have in the notation of the competition something like R1 minus R1, you can just throw it from the existing solution and just leave whatever else you have in the sequence. Because probably these puzzles were obtained with random disassemble, you actually have this in sample submission and also in some other public solutions. So I was able to optimize them a bit even with such a simple trick. And then there are others. For example, if you have in cube, not in other puzzles, if you turn the same face 4 times, basically you do nothing again. You came to the same state where you started. So you can just throw them out again. If you just apply this trick to public solutions at the sample submission, you don't find such sequences. It's not that probable, but there is another trick I'll discuss a bit later where it actually helps. There is some comment in chat. I can suggest making the solution and smooth. It's probably not related to my talk, so I'll read it a bit later. Yeah, and also if you have 3 rotations of the same face, you can just substitute it by rotation of the face in the opposite direction and gain some less number of moves. Yeah, so these are core ideas. They allow you to optimize solution a bit, but then I found a really smart idea in another discussion. And what it says is that if you have rotations on the same face of a Rubik's Cube, they actually commute. So it doesn't matter in which order you apply them. So for example, if you rotate the very right side of the cube, and then you rotate the left side of this cube, it doesn't matter if you do it in this order or in the opposite order, or you can also rotate the middle piece on the same face. You can basically switch them however you like. So what it means that, for example, R1, R0 is the same as R0, R1, or in general, if you have sequences of moves on the same face, like R something, R something, R something, so on, you can basically sort them or switch them within this sequence in any order you like. And that actually helps to apply all these tricks, because if you first had like R1, R0, R minus R1, if you just apply this idea, you can't cancel them. But if you know that they actually commute, you can cancel whatever you have within this sequence. And that worked really well for one optimizer, which solves any cube by applying the same algorithms that I used for standard 3x3 Rubik's Cube. You actually have like pretty long sequences of moves on the same face, and you can win like thousands of moves by applying this trick and the following optimizations. And another idea that I implemented, that was not my idea actually, that was basically stated in the description of the competition by organizers. So what they say that if you have here for 2x2 Rubik's Cube, if you have phase 1, then phase 2, and then some other phase rotation, and then you apply these moves in the opposite direction, it is basically the same as if you would rotate the D phase. It might not be clear why it is the case, so maybe it's better to show it to you on an actual cube. But essentially what it means that if you rotate, for example, all the faces, then you do this move and then you rotate it all back. It is the same as if you did just this move. So these full cube rotations basically do nothing. If you solve Rubik's Cube by hands, this is basically a free move. You can do it pretty quickly. But for computer, it would be 3 moves. Or for cube with a side 33, it would be 33 moves. And they basically do nothing useful. So you can try to look for sequences like that, full cubation, some move, and rotation in the other direction. Or you can actually say, let's just find these full cube rotations, so full face rotations, and then translate all the following moves. So for example, if you have F0, F1, R0, you just throw this out completely. You change this to D0. And then in the very end of the solution, to correctly rotate the cube, because this is important, you apply these moves. And so instead of this sequence of 5 moves, you would only have D0 and the opposite moves. I hope it is clear. If it's not, please let me know. So why it's cool?
Do we have
because,
similar relations for higher cubes?
Yeah, exactly. It works for any cube, basically. And more than that, you don't even need full cube rotations. Because if you have a Rubik's Cube with, let's maybe search for a bigger one. Yeah. So let's say you have a cube 5 by 5. If you have full face rotations, that's amazing. You can win 5 moves, basically. But even if you have a sequence like this, 3 faces rotation, this is basically the same as if you rotate these 2 faces in the opposite direction. So instead of 3 moves, you can do 2 moves.
Okay.
And for Rubik with size 33, instead of let's say 20 moves, you can make 13 moves in the opposite direction. So you actually win a lot. And
Excuse me, this may sound silly, but why do we not just consider the destination set containing not just one, but all of the orientations of the solved cube?
Yeah. I mean, yeah,
Why
it
bother
totally makes
with
sense.
counting?
Yeah, it completely makes sense, but then you need to find solutions that leads to one of the.
Okay, so you just eliminate the occurrences of full rotations composed of the moves in the entire, possibly very long solution.
Yes, exactly. So my idea was in optimizing the existing solutions.
And
what you
please do read my previous message in the chat. Maybe this might come in handy if it just happened so that you didn't think of it on your own.
Yeah, let's do it now. So you suggested making the solution n smooth, meaning making sure that there is no sequence of n steps shrinkable to a shorter move sequence within the boundaries of computability that are imposed by the available memory and CPU time, of course. Yeah, that's what many competitors did. They applied graph search algorithms. So one idea was to go through the whole sequence of states we have during the solution, then make n moves.
It would be best illustrated if you look at the picture which Alexander shown in the beginning of our meeting, where he's shown 2 big red radiuses and radii, whichever the proper plural form of that. And the problem is that those radii are bigger than the radius of the observable universe, even if you count it in Planck's length. And if you just reduce the radii, you will get less reachability than the entire graph. But you can make your solution somewhat smooth if you choose if you compose it from optimal pieces, and these optimal pieces are in fact n-optimal, so that there are no shorter paths between two points in the solution. Well, you already understand what I mean, right?
Yeah, and you're completely right. Other competitors also had notebooks similar.
It should be just one of the moves you should consider. Like maybe you should just. It obviously will not be enough if the shortest path is entirely different and is not close to the original solution. But then again, you will compose your solution by methods like what do we usually do for that? We do genetic algorithms to mix solutions. But for that, I think you will need at least 2 different solutions that are vastly different so that you could crossbreed them.
Yeah, I think next talk of Pavel will be closer to that idea. But yeah, I completely agree. Yeah, okay. So we are done with this notebook. Actually, one other comment. So what I suggested, remove this full cube rotation, so more than half cube
Also,
rotations. Yeah.
sorry for interrupting again, but finding something in smooth is one thing, and finding something in smooth after transforming that long solution is entirely different thing. Like, have anyone tried finding the solution after transforming the initial string of moves in different ways? Like we can always transform the string of moves and only then search for shortcuts that are provided by reaching with these radiuses from several points in the transformed solution. Like applying this technique is one thing, but applying it in tandem with your own techniques, other techniques, may yield even better results. Have you tried that?
What do you mean by transforming solution?
You already proposed at least several ways to transform the string of moves into another, possibly shorter string of moves by, for example, swapping the commuting moves. Like there are some moves that can be performed in different order without noticing any difference in the final result. But this transformation actually may lead to some solution, some better solution coming within reach for this and smooth method. Like some solutions were too far from each other. Some points were too far from each other in the initial solution, but they came closer to each other and became reachable within n moves, which was impossible if you just use the n smooth strategy without doing anything else.
Alex,
did anyone try
that in general, this is very low probability that we have a shortcut.
So the moves, you say you're telling me that the initial solution was chosen that way, that there were no
just generic solution,
simple shortcuts.
The number of states in the cubes, it's a kind of incredible.
Yes, that is quite clear. I'm not even thinking about that.
I don't know, there was a hill climber algorithm which our team members used, and this was somehow working, but still, okay, maybe we'll discuss this later.
Yeah, I agree with that idea as well. I also had a similar one, checking if the same state is visited twice during the solution, but now probability is super low throughout so many states.
Basically, what you're telling me is that the initial solution that you were given was not that bad.
No, it was terrible.
It was bad, maybe 10 times or even 20 times worse than people find. But the number of states, it's that much incredible that even this bad solution do not have a shortcuts.
So there are no simple shortcuts that are easily findable within that long solution. Like the solution is long, but it is not long enough to have obvious loops in it that can be get rid of.
Well, it seems so. It seems so. But well,
what's that? I can see scores. PCA.
No, don't look at it. I just wanted to visualize what you're proposing. So what you're saying is that we have a solution state where we want to go. We have initial state where we start, and then you say, so baseline submission kind of works somehow to that solution state, not in an optimal way. And you're saying that we can find shortcuts like this and make solution better. The problem is that the initial the sample submission that we have doesn't go like this. So there are no states along the way that are really close to each other. It rather goes something like that. So there are so many states that
that's a
the
good
probability,
visualization. It's a
the
good
probability that
visualization.
you will reach similar states is really low. That's the problem. So we need something completely different to find a better solution.
So the solution is not optimal, but it's far from having these close places at which you can make a shortcut.
Yes, exactly. It's not even the property of this particular solution, it's property of any random walk in the state in general. It's just too huge.
Yeah.
Okay.
Yeah.
Okay. So if you make some kind of random walk, this may beat this spiral structure you just. Fair thing is the spiral is two-dimensional, but I'm not sure it will work just as well if the spiral is not in 2 dimensions. I mean, it probably could work, but not that efficient. In 2D, you're bound to hit the spiral with the random walk, but in 3 dimension, I don't know, like, let's hear.
So like Alexander said, even for 3x3 Rubik's Cube, the number of states on the next move multiplied by 13. So there are like 12 possibilities to go in the wrong direction, and only one move will probably move you closer to the solution. So the probability that you walk away from a solution is much higher than probability of choosing the right, like the best optimal move.
So you mean the spiral is sparse enough not to have any close lines? I mean,
yeah, yes, I would say so. Yeah.
Yeah, quite clear.
Okay, if there are any other questions or comments, better to do it now, because then I'll start a bit a larger block.
No. I think so far it's clear enough.
Yeah, thank you for your comments. So the next thing I did for our team during the competition was solving so-called colorful cubes. I'll show you in a moment what it means. Here's a nice notebook, not from me, from some other wonderful person who visualized all the unique solution states. And some of them are normal. For example, this is standard 2x2 Rubik's Cube, but some of them are colorful. What it means is that each piece can have a unique color. Here, they visualized in different shades of, for example, red or blue, but actually each piece has its unique color. They are coded as N0, N1, N2, N3, N4, and so on. And there are some other striped kind of cubes. So this is a solution state that you need to reach. And for larger cubes, it looks like that. And it's not simply disassembled cube. You can't actually reach this state with normal Rubik's Cube. You have to like cut the pieces or recolor them completely. And the problem with these cubes, here is the colorful ones, and with big cubes, it looks even more beautiful. Yeah, so for example, this one, so this is a colorful 6x6 cube, striped 6x6 cube, and there are like large cubes. So for example, this one has unique color on every piece. There are also these types of cubes. And you can't simply input this cube to solver. There were some solvers available publicly that basically just apply 3x3 cube algorithms to find the solution, but they do not work with cubes like that, and especially with cubes like that. So it was not clear how to solve these cubes at all. And what I did in another notebook, I simply recolored them to be colored as a normal cube. So for example, here, if you have this kind of chessboard pattern, you can actually say, whatever, this whole face will be green, this whole face will be yellow, this whole face will be blue, and so on. And then you can actually input this into Solver, and it works. So it was surprisingly easy, I would say. You just needed to guess this recurrent trig. Here, it was more complicated because you can also recolor, say, okay, these pieces all have the same color, let's say green, these are all red, these are all blue. Now, please, Solver, solve it to me. It gives you a solution, and it puts all of the pieces on the correct faces. And also, there are corners and edges. They all are placed correctly after the solution from Solver. It is guaranteed. But the problem is that pieces on the same face can be mixed whatever like. So you then need to put them into correct place. I don't remember if I have it here visualized nicely, but yeah, this is how it looks in code. So colorful cubes basically have unique color on every piece. I don't really remember. Yeah, looks like I have it here. So here the solution already obtained from Solver after recoloring pieces. And you can see that edges actually solved correctly. We have N20s and 21 and 22 and so on. They are in the right order. This is also correct. But if you take a look at the inside pieces, they are not placed correctly. They should also be sorted, like N6 and 7, and 8 should be here, but it's actually here, and so on. So we need to find a way to move these pieces to switch them and not disassemble everything else. And this is a general problem with solving these types of puzzles. You don't have a clear metric of how solved the puzzle is, because if you just calculate how many pieces are on correct places, well, in the solution state, it's all of the pieces. In initial state, it's much less. But in between, you don't have this smooth trajectory. You go back and forth. Yeah, thank you for coming, John. Bye. I also have this visualization here. So in a baseline solution, you start with initial state and you have 21 piece not on the right place for 2x2 cube. And then in baseline, you jump and jump and jump, but in the end, you find solution state. So you have 8, and on the next move, you have 0 pieces on the wrong places. This baseline is terrible. If you take a look at the current top public solution, it looks much better. But still, you can see that here you make a move, and it basically does not improve number of pieces on correct places, and sometimes it even makes it worse. But this is actually optimal solution. You can't do any better. And if you take a look at larger puzzles like 3x3 cube, you also kind of see that you don't always go in a greedy way from disassembled to assembled state. You always have these jumps. And this is a problem. If you didn't have it, you could just use a simple greedy algorithm. But turns out that with smarter moves, they're called commutators for mathematical reasons, but actually Rubik's Cube community knows this term. even though they don't always know the math. But what this means that these moves only move certain pieces without disassembling everything else. So here it's visualized with highlighting moves. For example, one particular move. I'm not sure if it's written here. No, it's not. But anyway, you started with state n0, n1, and 2, and so on, all sorted. Then you apply some move, and only these three pieces move. Everything else stays the same. This is a sequence of moves. It's not particularly short. I think it has like 9 moves, but still, it's very useful. If you only apply these types of moves that swap some pieces and leave everything else in place, you can actually apply them and using this greedy algorithm that just takes the best move in terms of number of pieces in correct places, you can basically reach the solution. And what I am really proud of, I had an idea how to generate all these moves for cubes and also some similar moves for globes. That's another puzzle in the competition. Kind of analytically, I have some functions that basically search all these types of moves for you, and then I applied that for solving colorful cubes and also for globes. This is an example of such moves. For example, everything else stays in place, but these 4 pieces are swapped. Not all the moves I have move only 4 pieces. You can also leave only such moves, but in the book I found that some other moves can be useful. For example, this one, which is another move that only moves 4 pieces, and so on. So I generated that, and the next idea was to apply it, to basically apply graph algorithms to find solution state, but using not standard moves, but all these smarter moves. Unfortunately, it requires more computational resources than I hoped. Maybe because my implementation was not optimal. I did it all in Python, but for example, the winner used Rust, and some other people use C++. So maybe if I used another programming language, this approach would work. But what I find interesting is that even the winner found these moves using graph search. So he basically checked a lot of move sequences to find moves that only move certain pieces, and I just have a function that generates all these moves for you. Yeah, unfortunately, it didn't help us to find solutions for these puzzles, but still, I think it's quite cool, and it was actually quite interesting to think about it.
So these moves are kind of have a short support in mathematical language, so they move only a few pieces, yes?
Yeah, exactly.
So how do you use them afterwards? And so you found them, and what is the next step?
So first idea, it's kind of lazy, but it should work. You just run graph algorithms like searching a solution, for example, A star, but using not standard moves, but these permutations given by these moves. And it will already work better. But also, I believe there exists a fully algorithmic solution without this graph search. You just know that, for example, this piece needs to be swapped with this piece, and then I believe you can somehow select the moves that only moves them and leaves everything else in place. If I had another couple of weeks, maybe I would guess this algorithm, but I didn't have much time yet, and yeah, I just tried to solve it using path, so A star algorithm basically. But the beauty of these smarter moves is not only that they move certain pieces, but also that they commute with each other in many cases. So for example, if you have this move that moves these corner pieces, and then you have another move that moves these 4 pieces, you can actually combine them in a smarter way and get a new move. And sometimes if they both start with F0, for example, then you can just drop one of F0s. So you combine these moves, but the total length of the combination is less than some of these lengths. And this is exactly what the winner of the competition did. I didn't have time to optimize it, unfortunately. But that's, I believe, the best what you can do with algorithmic solution. Okay, was this clear for somebody who was not on my team?
Yeah, everything is clear.
Okay, that's good to know. Then that's basically all what I did during the competition. I also had some discussions and some notebooks like this one for visualization, but it's not that important. So if there are no other questions or comments, I can give word to Pavel.
Any questions, comments, suggestions, or whatever? Or we can move to Pavel's talk. Okay, maybe questions later. And so, Pavel, please start sharing and.
Mm-hmm. Oh, give me a second. So I hope you see something.
Yes, yes, it's okay.
Okay, so well, I'm gonna cover 3 topics here. I'm gonna continue the group theory like stuff, and then I'm gonna say about puzzles as linear programs, well, mixed integer linear programs basically, and I'm gonna cover a little bit about the reinforcement learning approach, which I well tried, but this approach really failed. This talk basically is upon my kernels, which are stated here. So I'll go to the main part of my talk. Here are some basics in groups theory. I'm not sure if I need to cover that, but to be sure that we are on the same page, let me just quickly remind you. Group is just something like integers or reals. Well, basically it's a set with some operation. This operation has some cool properties like associativity, and that the set some elements like identity element and versus for each other element. And here in the competition, we have some different puzzle types which can form different groups. The elements of the groups are basically just the collection of moves and their combinations. So operation is to apply moves in the order. Identities do nothing, and inverses are just the moves that we take in the inverse order, basically. A little bit on group presentations. Each group can be written as it can be described by its generators. These are the elements that will basically generate all elements in the group, and by the relations are just the equations that hold in the group. For example, Vladimir has just shown that in the cube puzzle we have something like this. If we apply F0 4 times, it basically does nothing. So this is just an example of the relation, and F0 in this case is just a generator. So as it turns out, if we know the structure of the group, if we know the generators and the relations, we can basically optimize any given solution. And in fact, a lot of like optimization techniques that were presented via notebooks, they all use this idea. In fact, there are a lot of relations in any group, basically, in any large group, and it's basically not that easy to find all of them. For example, if we have some element like here in our puzzles, this is, for example, this combination is also a relation, basically, and well, if there are a lot of like generators, there are a lot of so basic relations, and there are, well, might appear some new relations like this. So the key point is that there are really a lot of them. So it's not possible sometimes to, well, search for them, but we can try. It can be done with different computer algebra systems like SymPy in Python, or Sage, or Gap, or Magma. Well, there are a lot of them. But as I said, it's very hard. It's very difficult to find all of them. It's computationally costly, especially for the larger ones. But sometimes most of the relations can be found in like small groups. And for example, in Gap, which I extensively used, it's quite possible to find to find all of the relations. Well, in cube 2 by 2 by 2, or cube 3 by 2 by 3, for example. And one can infer some relations in larger groups by looking at the relations in the smaller groups. There is some relations can be sort of lifted to the large ones. And there is something in the chat. So the group is the product of smaller groups. The relations from those induce one in our big one, they do induce, but I suppose at least. But in our case, it's not that. I mean that the group, for example, for a large cube, is not the product of something and the cube and the large and the small cube, I suppose. But it's kind of true that the product of groups, the relations of the product is some sense the union of relations of smaller groups. But there might be some else, I guess, probably relations. But I'm not that sure about that. So as I said, it can be possible to find smaller relations. Again, another message. So we deal with subtler structure. Yeah. I mean, I suppose so. I mean, like, what I mean by lifted here is that, for example, we have some relation like, well, for example, we took just our black box like Gap or any other system that can compute the relations, and it provided us with some relation. For example, I don't know, it's just a basic. It's basically just some sequence of moves. For example, this one, I don't know, something else, blah blah blah, and in a smaller one. So we can just look at that and probably get some idea behind the similar relations in the larger ones. So that's what I basically mean. So yeah, in my well approaches, I was able to compute for small ones, and in some of my notebooks, in the first one, I suppose I provided the list of all relations in the res 6x6 group, I suppose, or res 7x7. There are really a lot of them. I mean, like maybe hundreds of thousands of relations. And in theory, as I said, it's possible to optimize any solution using them, but I eventually didn't create the possible algorithm to extensively use all of such relations. Well, but well, it's possible, as I said, to do that. Another topic on the group theory is the Minquist algorithm. It turns out that, well, to solve a puzzle is basically to factorize elements in this group. Well, it's in some sense, it's just a purely tautological sentence. And there is a Schwarz-Simms algorithm and Minkowitz algorithm, which is a pawn of that, I suppose, which actually, well, does it. And we had a notebook by Wissens-Gaetan, I suppose, that implemented this algorithm in SymPy and was able to largely optimize the solutions. I mean, he improved the public solution by quite large value. And it requires a base and strong generating set of a group. It's some mathematical things in group theory. Well, strong generating set, for example, is just as a typical generators, but they are a little different from that. And SymPy actually computes all of that. As I said, Wissens-Gaetan has done it, but it also quite computationally extensive, and it takes some time. But one can use, as I said, another computer algebra systems, for example, GAP, which can provide some faster algorithms. For example, GAP with that package called DNSS, I suppose, it computes the base and the SGS quite fast. It uses some random techniques to do that. The code with these computations are below. And well, we with Maxim, I suppose, well, he was in this Zoom meeting. We used the strong generating set and basis from the GAP to optimize solutions.
Can you repeat, please? What is a strong generating set?
Well, in layman terms, it's basically just, in some sense, the same as the generators, but a little bit different. So I can just give a definition about that, or I'm not sure if I can actually. But this is just a set that can generate all of the elements in some subgroup or given group. This subgroup is somehow related to the base elements. Base elements are the elements such that if you take an element from the group and apply it to the element of the base, it basically leaves the same. So in some sense,
well,
it's
maybe in the other words, it's something like it's easy to represent any element as a combination of these strong generators, or
yes.
Okay.
Easier as in shorter.
Sorry?
And by easier, we mean just shorter.
Not really, because the most shortest way to represent any element is to write it as a product of the generators. But it's not always possible, at least it's not always easily possible, if I can say so. And therefore, we need the strong generating set, and there are algorithms that can do this. Well, that's what I mean by easily.
It sounds like a decomposition. If we have a subgroup, or if we would have a vector spaces, it would be something like a vector space and it's orthogonal, something like that.
Well, any when we speak about some generators, there might be some analogy like this, and in this case, it's also possible to say about that. But as you said, in your example, it will be much closer to speak about the typical generators, right? These strong generating sets are not generators. I mean, there are generators in well, but it's not the minimal one. It's not the minimal set of generators.
Okay.
Yeah, so there's some larger set of possible elements that can generate the group. There's some in order to find it, you need to check basically that you have some subgroups. I forgot how you obtain them, and then you just look at the intersections, and then you at the group and some set, And if this intersection generates all that group with which you intersect, then this set is a return generating set. It's a bit like difficult to maybe get it on without like without something like written on the blackboard, but that is what it is.
Okay. Sorry, I see that Rob Pratt joined our webinar, so glad to see you here. As far as I understand, Rob is expert in this linear optimization problems, how to apply this to these puzzles. Pavel, if you can jump to this part, maybe great.
Sure. It's basically the next slide.
Oh, I'm right on time then.
Yep.
So Rob, we are very informal, and you are welcome to interrupt and comment and whatever any moment.
Okay. Yeah, thank you.
Yeah, well, okay, so the next topic is about the reformulation of the puzzles as integer programs. And well, to be on the same page, the mixed integer linear program is just a standard linear program, which is an optimization problem of such form, and with some constraints like on variables that some of them might be, well, should be integer valued. So some of the x's are just integers, or maybe binaries, so it will be a mixed binary linear program. Well, it turns out that one can reformulate our puzzles as wheels, and the reformulations is the following. So we need to, well, we need basically to think how can we encode the moves which are applied at each time step. We need to somehow encode the position in the cube, or in the puzzle, in any puzzle basically, and its color. So let's start with the encoding of the moves, which I need to take. So we can consider the following function, where, well, y, which well, goes from the product of some two sets, one blah, blah, m, where the m is the number of allowed moves, and the product by, well, their product by one blah, blah, t, where t is the max number of moves which we can allow to do. Our, well, basically the God number, if we can say so. And this is a binary function. I'm sorry?
Just a moment. So y will be okay. No, m number of allowed moves.
Yeah.
And we can define objective. So y, is it something representing a move or what?
Yeah, it represents which move is done at the step t. So for example, if the first move is done, then y1 at mt, then y1 of t equals 1, and the second, and all other moves are just zeros at the time t.
Okay.
Yeah, so this is basically just we need this stretch function to understand which moves are done at which step. And the abstraction function can be written as the following sum, double sum, y multiplied by t. We multiply by t basically in order to run the optimization. When we need to minimize this, we need to do the shortest number of steps, the smaller number of steps. So therefore, we need the smaller value. So we have some connection problems. I can't really see the chat.
We hear you. Okay. There is a question from Alex.
Okay. Is thou have a limitation? Well,
it's not maybe hardware limitation, but if we know, for example, the diameter or something, then we can that we can want to find the solution with, say, 100 steps, not more. Yes, so no, it's kind of
okay, understood.
If we don't find it, we can put it to 200. Yes, so it's a kind of you can cook it up as you want.
Yeah. Well, basically, you probably won't be able to put t as large as possible because that will blow the search space up. So you really want to be t as small as possible. And the smallest t you really want to incorporate in such machine is the God's number, basically. Is the diameter of the graph of the group. Well, yeah. So that's the objective function for linear program.
Yeah,
What
so-
about
Sorry,
Mhm.
before you go into the beyond the objective
Yep.
function, did you also try without the t coefficient in the objective? Because that's kind of that more natural choice. You're minimizing the number of moves. Both of them will
Mhm.
give you an optimal solution, but I just wonder if you tried both ways or not.
Well, I actually didn't try it.
Okay.
I suppose. Yeah. I didn't try because the following I'll show some constraints, and some of the constraints they one of the constraints is the following: we need all y's to be 1 at the same time. So if we don't have such constraint, well, actually, I actually tried without t, and I tried without this constraint, but the new program went very well. It
Okay.
wasn't very well because it just put everything 0 and does nothing. Yeah, so in order to make some moves, we need some constraints, like sum by all moves at a specific time step should be 1. And if we do such constraint, then we really cannot minimize the objective function without this t. Well, I suppose it will be much clearer when I come to the constraints. Well, in order to encode elements of puzzles, which are colored by some colors, we can use the following function. It's again a function on some elements on some sets, well, one blah blah tn, and again one blah blah t, which basically just says which element at which time step is colored in which color. Well, that's basically it. So the main thing is constraints, and well, here they are. The following constraint I was using, actually I had another variable which I really don't use. I tried to use it, but the solution was infeasible. The problem was infeasible, so I decided not to use it. And well, constraints without those variables, which I haven't really mentioned, are the following. We want all the positions at the time step to be, well, initial state. At the last state, at the last time, we want all the solutions to be a solution state, all the positions to be as a solution state.
So I thought initially we have y, which describes the moves, and when x appeared, which describes the states, it's
X appeared. Well, I introduced it here.
This is the information on the states, but it doesn't enter the objective function.
Yes.
Only y enters the objective.
Yes.
Okay, I see.
Because objective function is basically about the moves.
Okay.
We are not really, well, at least in my formulation, I've seen there are some others, but in my formulation, I don't really use it because, well, we need to minimize the number of moves.
Yeah, okay. Let us go to the next slide. So
the next slide is about constraints. So the first two constraints are, well, trivial. The last one is what I was talking about. If this constraint should be like done, therefore we can't really drop the t out of the objective function, because otherwise the function is not minimizing at all, because at each time step there should be at least one, there should be any move, and therefore the value is not minimizing.
This should be less or equal to 1, right? At most 1
Oh,
move
yes,
per step.
yes, indeed. But yeah, this should be really less or equal to.
So where the
Oh no, actually it should be like equal.
Equal if you use all the steps, exactly. Yeah, but if you're trying to minimize, then you want to allow the possibility of not performing a move in some step.
Yeah, indeed. So it should be like less or equal to.
Where are the description of the moves? So moves are certain kind of given to input.
Yes.
Where is
so I haven't really mentioned about this in my presentation. Here in the under the sum sign, I have some set called A by 3 elements, FRC. Well, if I see adjust the coordinates, oh, sorry, there's some typo in my notation. My x function is in 2 variables here and in 4 variables here. Well, FRC is basically just the index of an element, so it should be not I FRC but a of y. Well, this is well, this are the set I a of y is the set of moves that well that that can be applied to an element I and it will be moved somewhere. It's not so. This are the elements of the complement of the stabilizer group of the stabilizer of this element. Well, basically, well, let me just write down that A at the point, well, I is just the set of elements F in our group, such that F of Y is equal to I. So, and here the information about the moves is incorporated in the linear program.
And so, if you say in the words, how to describe this, for example, the third solution?
The third constraint, you mean?
Yeah, so no constraints, right?
Yeah, it means the following. If well, let's recall that this variable y basically indicated that the move is done, and then the move m is done. So suppose y of mt equals to 1. Then action m is done. Therefore, the position element at the position element y is moved to some other element, which is denoted as ym, and therefore its value should be its value, which is the color, right? So its value should be equal to the value of ym at the next step. So the step t plus 1. I hope you see that. So if a move m is done, so therefore we have such relation, such an equation. Otherwise,
and then M is what? It's a matrix, or it's a I don't know what is.
Oh, you mean
the big M?
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 The big M is just a big constant in order to make this machinery, make this linear programming machinery. As I understand, I'm not really well a great expert in linear programming, and I suppose it's just a basic way to somehow rid of the equality and make all of these constraints as inequalities. I suppose it works well better. I hope Rob can say something about that.
Yeah, so if we just look at those two constraints as a pair, the third and fourth constraints.
Yeah, they're basically just from the pair, right?
Right, as Paul mentioned, if YMT is 1, then the part with the big M just cancels out, and you have less than equal to and greater than equal to, so you get the equality that he described. On the other hand, if YMT is 0, now by the choice of big M, these inequalities are redundant, so they don't enforce anything. So,
yeah, so well, if y is 0, then this value is very, very small, and therefore it doesn't really enforce anything. And this and this value in this constraint is really, really large,
right,
due to large m. And similarly, the following two constraints in some sense the same, but they say that well, let me recall that. Well, they say that any other move isn't really done. at the. Oh no! Wait.
Yeah, you can think of it as two cases again. So if that sum of y is 0, that means you're not performing any moves. Then the parts with the big M drop out and you get equality again. Then
Yes.
the current color is the same as the next color. On the other hand, if you do perform some move, then that sum of y's is going to be 1 because it has to be at most 1, right? So it's either, and again, the big M's make those constraints redundant. So it's really just two cases to consider. Sum of y is 0 or sum of y is 1.
Yeah. So that indeed, if the move isn't done, so there should be an equality here. So I hope it's clear. There any other like comments or misunderstandings?
So
one comment. Oh, go ahead.
Is it something like a standard, or this is you found by yourself, or you kind of motivated by some notebook or whatever? Where did you take?
Actually, I found it on the internet.
Yeah.
And I somehow modified it. Well, I modified it by the by using another variable which I haven't really described here. Because because this I wasn't really was able to use the linear program with that other variable which I haven't really introduced here.
Yes. So it is standard. They call these big M constraints. So if you look up big M constraint, you'll see a lot of information like that. This is a standard technique called big M constraints.
You can send in the chat the name because I cannot.
Yes. Big M constraint.
I see. Okay. Thank you. Okay. And this works for kind of any group, so we can take any moves and this.
Yeah, I mean, it's even beyond groups. I'll put in the chat too, kind of a general formulation. You want to say that if y equals 1, then you have some function of x less than a constant. And the way you do that is to rewrite it as this big M constraint that I'll put in the chat as well. So that's the general technique where y is a binary variable.
As far as I remember, in your write-up, Rob, you mentioned 3 different ways to reformulate as this.
Yes, this is close to the second way, to formulation 2. There are 2 changes that I had. One of them is that the objective, like I mentioned, I didn't have the t coefficient. I'm just trying to minimize the number of moves. And the other way is that I explicitly introduced a trivial move, which does nothing. It's like the identity permutation. And by doing that, you can kind of unify these constraints. You can write that pair of 5th and 6th constraints on the screen now are just a special case of the 3rd and 4th constraints if you consider the identity move. So that was just a way to kind of simplify the formulation a little bit. So you have 1 extra move in your set, but it doesn't do anything. It fixes every element.
I had such an idea in mind, but well, my realization, it seems like it wasn't really perfect, and I wasn't able to, again, solve any problem with such identity element.
And the other change is that it means that sum of y's, your final constraint is exactly 1 because you're performing some move every step. It might be the identity move.
And in general, how effective this technique is expected to be? Can we solve big puzzles, or it's a kind of medium size or small size?
It can be used only for the small puzzles, because the search space grows, I suppose, exponentially with the large puzzles.
Yes,
therefore,
definitely.
we can't really solve any puzzles that are quite large. Only the smallest one.
Okay, I see. Okay, thank you.
But still, the idea is kind of interesting because, I put it in the last slide and this topic. We can probably improve the the speed of the solution. Well, we can probably improve the way we solve these puzzles by some neural networks that are designed to tackle some problems in combinatorial optimization. There are a lot of like papers on that. Well, some keywords are NN4CO, I guess. And I know that some GNNs, well, one can use GNNs in order to solve some MILP problems. And well, it worked quite well, as I know, but I wasn't really able to try it in the competition.
Another thing you can do on the larger puzzles is to just consider a short segment of moves in some given solution and ignore all the rest and just try to optimize that short segment.
Yeah, that's a good idea. Well, as I said, I had some variable, some extra variable. This variable was designed in order to incorporate the information about wildcards, about the mistakes we can do in our solution, in our solutions of the puzzles. And there were some more constraints. I ended up with extra 4 or 5 constraints in order to make all this machinery, but still, as I said again, I wasn't able to provide some good solution. Well, the problem wasn't feasible, so there was no solution actually with that given extra variable. So that's it for that topic. The next one is about reinforcement learning. I had not really a lot of attempts at it, so I have very little to say about that. But well, as I suppose everyone knows, there are a lot of papers on that. I forgot their names, but there were some famous ones which were tried to well there were some kernels on the Kaggle that tried to use some alpha puzzle or alpha cube, I suppose, some network, some approach that is quite popular, but it wasn't really well working. Well, anyway, there are a lot of like papers on that. Both model free and model based approaches. Well, I tried model free approach and I failed, but I've learned a lot of things from RL, so that was my main motivation to do that. And I think that the main problem with that is to properly define the reward function. It correlates with what Vladimir was talking about the way to estimate how good we are at a given point. Because we can't really say that we are approaching the solution, because after each step in the best given solutions, at each step which we are doing, the number of similarities may vary, and it's not really decreasing. So this is the main problem here. Well, my attempts were the following. I tried just to reward -1 for any move. I tried to somehow compute the difference and the similarity and multiply them by some constants. Well, I tried Jakarta index that was suggested by Alexander in some kernels. And I tried to use just the number of moves minus number of moves, which are provided by the Rubik's Cube solvers. It's very computational costly, but I tried to do that. None of these approaches went well, as I said. So that's it on this side. So that's it on my side. So if you have some questions, please feel free to ask.
There is a question in the chat. Alex, maybe you can ask it by yourself.
I see. Is there a possibility to represent the moves and the states in a way that would render the cube rotations indistinguishable from each other to walk away to a smaller group? Well, I don't know actually.
Because that is not so trivial question, and of course, walking away to a smaller group will prove helpful, obviously.
Well, yeah.
And obviously, there are states indistinguishable from each other if we speak real cubes, not just the representations. Like, it's the same question as reducing the fractions to simple fractions that are irreducible, so that the denominator and the numerator have no common factors. Like, similarly, if we look at the cube, we can rotate it, but the cube is already solved and that is not changed. Can we somehow represent the puzzle in a way that the rotations of the cube will not be in that representation? Because this way we will store less information in the state. The space of states will be smaller, considerably smaller, and the search will be faster, and we will be allowed to reach further from our states with our, how do I say it? With our radiuses, if we consider my previous terminology, but with any method that performs any search, we will be able to reach further, because there will be lots of states that will become indistinguishable. Like, is this even a possibility? Like, I'm asking those who are already familiar and experts on the subject, because I am clearly not.
Well, I actually don't really know if it's possible. Well, you mean the cube
But the
rotations?
idea is simple and crystal clear to you, right?
Not really. Could you please repeat it?
Like, our representation is not optimal in the way that several states, several different from our representations POV states should be considered equal, but they are not equal from just the notation view. Like,
So you mean
notationally,
that
they are not equal, but the cube itself is already solved, no matter how you turn it around.
So you mean the cube rotations in, well,
information
it's
is
like cube
part
rotation in the
of
R3, you mean?
Our information contains redundant pieces about the cube orientation. And the question is, can we represent our puzzle in such a way that its spatial orientation will not be stored in the moves representation, in the state representation? Like,
yeah, I see.
Because if we do that, we will significantly simplify the task, the computational task, I mean.
I don't think it's significant, because you have the group of rotations, it's just 24 elements, and here we have Googles of elements. So if you divide Google by 20, this will not change much.
Yeah, but this will change much, because the radiuses that are reachable will grow 6 times because of rotations, or maybe I count wrong.
Yeah, I think it's just a factor of 24. So it does reduce it, but doesn't make a difference between the astronomical and not.
I also suppose that it won't even help us in some examples, of puzzles. If you remember, there were some puzzles that were colored uniquely. So basically, we really didn't have any color. We just had the code of the position at which we have to move the elements into. So basically, well, there were some puzzles that are not colored in 6 colors. There are puzzles, 0 colored in 24 puzzles, and 24 colors, or even more for 8 colors, and so on.
what I was saying was that perhaps having less information stored in each state and in each move may lead to some shortcuts becoming available just because they will fall into formal rules. Like we will see more formal rules when there is less distinguishability between the states.
Mm-hmm. Yeah, well, if there were some shortcuts,
Sir,
then
my
we will be
English
able
is
to.
failing me. My English is just failing me. I'm trying to formulate what I'm seeing from this puzzle, but my English is just failing me. I'm at loss of words.
I suppose
sometimes.
that such shortcuts can be found using some computer algebra systems. So if there's some, well, there are some such shortcuts, and there are, of course, the equations in our group, so there are relations, and they can be found with the relation search technique, some like
In
methods
short,
of gap.
I'm just saying about whether we can or cannot try to account for symmetries in the group.
It will not give us, Alex, no, kind of, if you divide Google by 10, that doesn't change.
Yes, that much is clear. I mean, but we have local rules of transforming the solutions, which do not look far from the point at which we are applying our simplification. And these rules, the amount of such rules may increase. Like we will be able to do more improvements locally in some parts of the solution, should it be represented in a way that accounts for symmetries. And I suspect the group in question to be quite to have some symmetries to work with. Well, at least the spatial ones are obvious. So I'm just thinking, did anyone perform the analysis of symmetries and how it may reduce the computational burden? Because it's not just about dividing Google by something. It's about the procedures we do to simplify the smaller parts of the solution. Because when we search for these simplifications, we are always bounded by how deep we can search for simplification formulas. And we can find more simplification formulas if we search like 6 or 7 or maybe 10 moves ahead. And if just improving our representations in some way would allow us to search not 10 but 12 moves ahead. Right. For some efficient formula, it may come in handy and provide us with some rules that we may apply to find more efficient solutions. Yeah, my English is failing me again. Sorry.
No, I think I understand what you're getting at. It's like all the different states fall into equivalence classes.
Yes, exactly. Yes,
they're equivalent
yes,
if you can rotate the whole cube.
Of course.
And so you're trying to collapse the state space by replacing states with one representative per equivalence class.
Of course.
So that might help the search. The thing is, in the end, for this competition, the puzzle's not considered solved until you've actually rotated the cube into the explicitly specified state, as part of the input. So there will be a final step to get it into that state, but it might help you. Yes, that's right.
Plus 6 moves.
That's right.
But how long is the solution to begin with?
Right. Yeah. For a very long solution, plus or minus 6 moves doesn't matter. Mm-hmm.
So plus 6 moves might be a good trade-off for whatever it might provide us. Like if that helps us to reduce the size in half Well, then I don't care about 6 moves.
Yes.
If everyone gets that, excuse me?
Попросил тебя,
Number?
мне пообещала, попросил тебя сосать, а в итоге наебал.
Меня сосать, да я тебе не сказала. Сосать, да я тебе сказала.
Попросил тебя сосать, ты же мне
Девочки на входе, уходи дороги, поджигали груди.
Okay, guys, you have seen the Zoom bombers coming. That it's like that. So we are lucky that they came at the kind of at the end. So when we almost finished, and typically they come many of them, but now it was only one. So now, just sorry, you can unmute yourself. So I removed this participant from the chat, and now the problem is solved.
All right.
So that's a kind of Zoom bombing.
Okay.
Since we put the link, Zoom link, at the publicly available, then
I didn't do that.
sometimes this happens. Okay.
All right. I think I'm already reading what John Mitchell wrote. Yeah, yeah, that's exactly what I'm saying is just we should consider taking symmetries into account. Like, it may help. It does not just boil down to dividing astronomically large numbers by 6. Like, we're talking about deducing optimization rules, and those rules may come into reach when we increase our depth in our research ever so slightly, maybe even by 1. But that's just, of course, my hypothesis. I didn't check it, of course.
Any other questions, comments, suggestions, whatever? So my question was, so I think, so the solution seems to be not very optimal, even the final solutions. I think Rob made some estimate, which is kind of minimal number of moves possible. But as far as I understand, the gap between this minimal and the current solution is quite big. Am I right?
Yeah, it's about an order of magnitude. I was getting around 4,000 as a lower bound from
So guys, what problems are we talking about as being a long way from optimal? Because there's a lot of different problem classes in the 398 that we were asked to solve.
Yes, and some of those classes we do know optimal, like for the Reese 6, 7, 12, 21, all the cube 2s are known to be optimal. But for the rest, I don't think anybody has claimed optimality. But
even, for example, the first case is 4x4 cube. So the diameter is not well known, but there, I think, very sharp estimate. But if you take a 5x5 cube, then this estimates lower bound and upper bound became, the difference is going bigger and bigger, each kind of with each side of the cube. And so I think it's quite interesting to understand what we can achieve. And for globes, if we have globes, so there is no theoretical estimates as far as I understand.
So can I ask something else? So in our actual competition, the globes were fixed in a strange way, right? Such that if there was a middle layer, the middle layer didn't rotate properly.
Yeah.
Does that matter in any way?
I mean, it's still a valid puzzle, but if somebody has studied, the actual physical puzzles and has some bounds there, they wouldn't be valid for these messed up ones.
Yeah.
Well, I don't know. For me, it's a kind of group theory. It doesn't matter the mechanical implementation exists or not. So I think these questions about the diameter is very interesting from a mathematical point of view, just by themselves.
Mhm.
I think that to obtain some theoretical estimates for the globes, it should not be that much hard. So, and we plan to think on this and maybe discuss some time later. Because as far as I understand, for cubes, this estimate n squared divided by log n, it can be derived heuristically, not in a difficult way. So I think for globes to guess at least the asymptotics of the diameter should not be that much hard. Of course, precise estimation should be difficult, but just kind of as a kind of approximate something like. So for globe, we have two parameters, A and B. Well, no, something, I don't know, I plus B squared divided by log of A plus B, something like that. I think it should not be that much hard to derive. And then it would be kind of interesting to compare what we have, these practical algorithms to compare with kind of theoretical estimates and probably to get something. So that's a kind of plan.
Well, the other interesting thing about it is that a very large proportion of the total moves of most team solutions are for just the last 17, or if I ordered the puzzles by size, so the biggest ones are at the end, more than half the moves typically are for the last 17 biggest puzzles, which are big globes and big cubes of 19 or 33. And I mean, the small amount of analysis I've done, I don't really think there's an enormous amount of scope to make the solutions a lot shorter for the smaller puzzles. I mean, we have empirically quite a lot of different teams' answers to them. If you take the best answer, you get a total of just under 4,000 moves, 3,700 moves for all the puzzles of diameter 50 or under combined. I believe that's all the puzzles of that's all. I think it's all the puzzles of 35 or under combined, and around 5,000 moves for all the puzzles under 52. So I mean, they're not. I don't imagine that those are anything like an order of magnitude improvable. They might be improvable by a few percent, but it looks like there might be scope for non-optimality much more in the larger puzzles.
Yes, I agree. Yes, completely agree. Well, I'm interested in the machine learning approach for this, but I'm not sure that machine learning is easy for the large puzzles. So at first I want to try something with, so for small puzzles, I've done it during the competition, it was okay, but for medium size, it was already a problem. But I hope we can a little bit resolve it, at least if we have more time now. And okay, I don't think that we'll get a great improvement for the small, medium size puzzles, but still I think maybe some improvement is possible. I know, Rob, and from your point of view, what's your opinion? How difficult is it to kind of improve some kind of puzzles?
I mean, it was very difficult for me. So, and the MILP approach is where I spent most of the time, just because that's my interest. So it really is not competitive for the largest ones. I was more trying to see what was kind of the frontier of what was the largest puzzle that could be solved in a reasonable time with MILP approaches.
Okay, thank you. Any other questions, comments, suggestions, whatever?
Well, I really feel that using the MILP approach and using some specific neural networks, one can achieve some decent quality on some large puzzles. But again, one need to generate the data set of the MILPs and the solutions. So this might become a new problem for that kind of approach. But I still think that this neural-based approach is quite strong in this case.
Yes, yeah. Oh.
I have another little, maybe silly question, but I think I'm going to ask it. Is there an algorithm for finding a solution without caring about its efficiency? Finding a solution fast without caring much for its efficiency in those groups?
No, I don't think so.
Well, one can use the min-increase algorithm I mentioned before.
It will guarantee you a solution, but it will be very inefficient, right?
I don't think it's guaranteed to be the
I
shortest.
suppose so.
No, I'm not even speaking of its shortness. Like, I'm only speaking of whether it is easy to obtain any kind of path between two given states of the cube.
I feel that it might help. I mean, if one is given by the basis and the strong generating set, one has to then build the table of closets or whatever it's called, and they feel that it's possible to obtain some solution. It won't be optimal, of course, but
the thing is, I'm thinking of genetic algorithms here, because if there are means to generate solutions and parts of solutions rather fast, I mean, so that we don't have to wait for a single generation of genetic algorithm to be processed, then perhaps it might be fruitful to try and apply the genetic approach here.
Well, I mean, one thing you can say is, for the competition, at least, we already have a solution for everything, right? I mean, obviously not for the general problem of any cube or any globe or whatever, but for the competition, we do have a solution, which we all, I think, or most of us suspect, is a kind of random walk away from the solution state to some arbitrary state that's then taken as the initial state, and then that random walk has been reversed to generate the sample solution. That's probably what most of us suspect has been done, I think, from the discussion on the forum, although I don't know that, right?
So so the competition puzzle, you have the shortest solution proven unknown.
No, we don't have the shortest solution. I mean, only for some of them. We have a long solution, which we know for everything when we start, which you could improve by. I mean, in principle, you can improve it by a genetic algorithm. It doesn't sound like an efficient way of generating the best solution, right? And I mean, when we actually did it in the competition, you know, our team. I mean, the team that Alexander and Vladimir and I were on, we were rubbish at the bigger puzzles, right? We were competitive with the best teams at the smaller puzzles, but at the bigger puzzles, our only approach was to try and really shorten the sample solutions, and we got some shortly. But even if you reduce them by a factor of 2, you still got an awful lot of moves there.
So what I was thinking about is to try and apply genetics to improve the set of solutions if the set is big enough. Like if you have several ways to reach the point, I mean, this is the same thing to reach the starting point from the puzzle, or to reach the puzzle from the starting point. If you have several known ways to reach the puzzle point from the start, then perhaps you can cook up some way in between. If you try to connect parts of these ways in genetic manner, like if there happen to be shortcuts between parts of between several different parts of several different solutions.
So someone, it might have been Vladimir, I can't quite remember 100%, said that they thought that it was unlikely that it would be easy for, like, if you took 2 different solutions, that they would intersect. So I think that kind of suggests that it's not trivial even having one solution to find a meaningfully different solution. And it's also unlikely that 2 sort of arbitrary solutions from the big space would necessarily come close to intersecting it in any point.
So generating a good set of solutions, if you were given just one, is hard enough.
Probably, I think.
I mean, I somehow suppose that you can come up with numbers of solutions, however inefficient they might be, but you can have a good number of them. And it seems that was not very good presumption from me.
Well, I think it might be true for the smaller puzzles. Well, I'm sure it's true for the smaller
yeah,
puzzles,
of course.
but not
of course.
for the I don't think it's necessarily true. I think the argument was that there was a huge state space for the biggest puzzles, and the starting positions are probably fairly arbitrary random points in the space of states that happen to be reachable by some random algorithm from unwinding the original ordered state. That's so the broad consensus.
So we cannot find the solution for a random point in the space shortly. Like to find a solution for a state we didn't previously reach by a random walk and recorded our steps is a hard task.
We think so. I mean, it would be really nice if we could persuade 1 or 2 of the top teams, if there was going to be a serious effort to improve the solutions, because clearly some of the top teams did very well on the larger puzzles, and it might be, you know, the teams that finished in the top 20 or 30 places, a lot of them did seem to do a lot better than the people on this call have done, right, on the bigger puzzles particular. And it might be really helpful to try and reach out to some of these people and see if we could get them to be interested in being involved in something like this.
I don't think I will be able to. It's just that I'm not an expert on the subject. Like I will not be of much help because I never participated in anything like this, and I'm a stranger to most of the techniques you use. I'm just curious enough to try and come up with some approaches that might be helpful from my stranger point of view. And from my stranger point of view, I somehow thought that perhaps if you have an algorithm to cook up some more solutions as an extra to the one you have been given, then perhaps you can cook up some more solutions by the way of genetics, and those solutions might somehow converge on onto the better ones if you consider the proper transformations for the genetic algorithm base. But if you say that generating solutions for bigger problems, bigger dimensionality is a problem itself, then probably this will not work. Do I understand you right that just calculating one solution for some unknown state is already hard?
I think yes. I think it's maybe even in P-hard problem or something.
I mean,
so-
that's essentially the original problem, right? These states are somewhat arbitrary, and
No, I didn't mean the shortest solution. I mean anything that will lead us to the initial state.
Well, imagine we've got several solutions already now, built up to the competition, and they were not always easy to come up with. But suppose you start from that point, you've got a set of solutions, and some of them might be similar to each other. But
yeah, we have about a dozen solutions
Right.
available for all the problems. Yeah.
So what can you do with that as your population with the GA to try to combine them somehow to get a better solution?
I could try to find the points at which the solutions getting close to each other, getting close enough that we could.
The space is very huge, astronomically huge.
Okay,
so
so
your
all right.
solutions, they do not intersect.
And I'm not even hoping for them to intersect. I just hope that they might come close enough so that 2 points.
I'm sorry, but how do you define this metric in which you measure the closeness?
The closeness is already these n balls, which I proposed earlier. Like we can always propagate.
Well, the n balls are just an illustration of this principle.
But they are probably too small to reach any other solution. That's what you're saying, right?
Yes, because it's a kind of exponentially Google, yeah, and your length of your path, which maybe 10,000, 100,000, but 100,000 comparing to Google is zero.
Yes. Okay. What I was saying was basically we draw not a line through the space of all states, but a huge, a thick cylinder. And this cylinder you're telling me is not thick enough, not even close.
Yes, of course.
Right.
All right. All right.
What is a cylinder in these terms? I mean, we don't really have some metric that is supposed in the group. We can't really draw a cylinder.
I think the cylinder comes from taking a given solution and at each state in that solution expand, just breadth first or something.
Of course, you got me right. Yes,
Okay.
you got that right.
But still, you have to go a very large depth to be able to get an intersection with it.
Yeah. So the solutions that might comprise the basis set will not have points that are close to other solutions points. Like they will be entirely different, to speak in simple terms.
Yeah. Because it's an extremely huge space. All your 10,000, 100,000, it's just...
No, I understand.
Even you make thicker, so you can estimate. Okay, for example, for standard cube, it is factor of 13. So if you make it thick,
I know of the huge numbers.
It will be still kind of zero comparing to all the space we have astronomical. So
here might also be a problem. Well, we might also have an obstacle in the work problem. Basically, if you just imagine this cylinder, circle, or whatever, via your breadth first search moves, and you go in breadth 5 or whatever, you might find some relations which basically cancel each other out, and you'll get some word. And after your moves from the initial state, I mean from some solution to, if you apply some moves, you'll get another sequence of moves to the solution, and you're not able to check whether whether this new solution is in your cylinder because of the warp problem, basically.
Okay, but let's okay. I'm going to show another train of thought that just occurred to me. But okay, you asked how I generate even one solution from this basis. We should remember that all solutions start from the single point, and all solutions converge to a single point. And in the beginning, all the solutions are close enough to be reachable. So we can always generate worse solutions, but only slightly worse by intermingling in the beginning or at the end. And these new solutions may still add up to a bigger basis for our genetics. And this way we have different solutions, but that are only different in the beginning. That are some combination of the initial set of solutions for the beginning part. It is probably worse than the whole solution that is given. That is probably worse than any of the basis solutions that we have, but it is different, and that's what our primary concern is. It is a different solution. And then it may participate in genetics further. Like we can try and optimize the transition between the beginning parts of the solutions that we use to produce this new solution. And then if we try to mingle with it, add it to our basis, just maybe we can reach further if we then, for this new solution, find some new closer points that are outside of this starting ball from which all of the solutions diverge from point zero. But after getting this new solution, maybe it gets somewhere close to other solutions, slightly further than these initial first n steps. And this may get us some new solution that still stays close to our initial set of solutions, or perhaps, if we're lucky, even better, and provides us some variation, some room for changing our solutions further. Like we will probably get solutions that way that vary not how do I say this? That vary not so big as to become out of reach from other solutions by our search techniques. You're still with me? Because my English is always failing me, and perhaps I'm just talking nonsense.
Not sure. But maybe let me clarify. So, Pavel, do you know, so as far as I understand, to find the optimal, the shortest solution, that should be NP hard. But to find some solution, maybe something it's simple, or even algorithmically possible. What you said with this strong generating sets, possible, yes?
Yeah, it feels like it's possible to generate some solution with that.
Will this? But yeah, I already read that. Sorry to interrupt you. I read that. Thing is, these solutions are not even guaranteed to be of the same order of magnitude as the initial one in terms of its wellness, like in terms of the number of moves in it. Right, so we are given a solution of 100 moves, and the algorithm gives us 1,000 move solution, and we are probably not gaining much from it.
Yeah.
Okay, but let's consider what Bob, Rob advised earlier, that we can get several solutions to begin with that are of similar order of magnitude if we count the number of moves, and start varying those a bit in the beginning or in the end, or both. We can do that because we have several solutions, and we can transform from one solution to another. We can still get from one solution to another if we haven't wandered too far from the initial state yet. Because if our solutions are 5 moves from the initial state, both, then it's obvious that they are not more than 10 moves away from each other, right? Just from pure logic. And if they are not more than 10 moves away from each other, they are probably less than 10 moves away from each other, since they are all came from point 0. And if they are considerably less than 10 moves from each other, then we have another solution to add up to our mix. And when we
let me, for example, I mean, I think we should think not in this way. The key point is this diameter or God's number. For example, for Rubik's cube, it's say 20. That means any path which is 21, 22, it can be shortened. But as far as I understand, this shortening will be completely different. It's not local. So you have 21. It's possible to make it 20, but it is kind of very different will be the sequence of moves.
Yes, but the genetics work in the way that it will keep several different species that are vastly different from each other, but both surviving because their value is close to each other. Like you will keep both populations intact, and in the end, one of them will reach the God's number and will be declared optimal. Like the other solution that is very far from the optimal one is not dying until you reach, I think, until the first one reaches the actual number of 20. Like that's why you take a lot in the population before the genetic algorithm begins to produce any good results. So
I think discuss this later. Okay, so
okay, never mind. It's a very, very, very simple thought. So perhaps somebody else already came up with the thought. And since we don't read a lot of papers regarding genetics helping in this particular problem, it probably will not help. Like, I didn't say anything extraordinary here. So if we still don't see any papers on the subject, probably I'm just talking nonsense. So okay, don't mind me.
Any other questions, comments, suggestions? Okay, maybe then we should finish. So thank you very much, everybody. Thank you, Pavel, for presentation. Thank you, John, Alex, for coming. And so video record will be on YouTube, our YouTube channel, I hope tomorrow. And so good evening to everybody. Maybe let's keep in contact and discuss these problems further. Hopefully we can find better solutions. Okay, so have a good evening.